Let's start with a simple picture. Take any liquid at rest and the surface behaves as if it were a thin, stretched elastic sheet. That property has a name. It is called surface tension. Physically, the liquid is constantly trying to minimize the area of its free surface, the part exposed to air. To measure that pull, we draw an imaginary line on the surface and ask how much force acts across it per unit length. The answer is the surface tension S in symbols. S equals F over L, and here is a quiet but useful equivalence. Because work is force times distance, the same quantity also equals work done divided by the change in surface area. That is why the SI unit can be written two ways, newtons per meter and joules per square meter, and the numbers come out identical. Two units, one meaning. Also notice that S is a scalar. It is a molecular phenomenon, because each molecule sitting at the surface has fewer cohesive neighbors than one inside the bulk, so it is pulled inward. And critically, S depends only on the nature of the liquid, not on how big the film is or how long the line you drew happens to be. The dimensional formula is mass times time to the -2. Now we can answer a very natural question. Why are small drops round? The answer is geometry. For a fixed volume, a sphere has the smallest possible surface area. Since the liquid is always trying to shrink its free surface, an unconstrained drop naturally settles into the shape that does exactly that. The same physics shows up everywhere you look. A fine stream of water breaks into spherical droplets. Mercury spilled on a flat surface beads up into near spheres. A soap bubble that you poke rounds itself off again within a fraction of a second. Different scales, same principle. When a liquid surface is left to itself, it minimizes area, and a sphere is the area minimizer. To go deeper, we need two names. Both kinds of forces involved here are van der Waals forces, and both fall off roughly as 1 over r⁸ with distance. Cohesive force is the attraction between molecules of the same substance. Water pulls on water, glass pulls on glass. Adhesive force is the attraction between molecules of different substances. Water pulls on glass, ink pulls on paper. Throughout this chapter, what really matters is the ratio of adhesive to cohesive force. F sub A over F sub C. That single ratio decides whether a liquid wets a solid, and it will come back to us in the next deck when we talk about the angle of contact and capillarity. Hold it in mind, it is a thread that runs through the rest of the chapter. Where does surface tension actually come from? At the microscopic level, every molecule can only attract its neighbors out to a finite distance. That distance is called the molecular range, of order 10 to the -9 meters in solids and liquids. Beyond it, the intermolecular attraction is negligible. Now imagine a molecule sitting right at the free surface. On the air side, there are simply no neighbors within range. On the sides and below, it feels the full pull of the bulk. The result is a net inward force. A molecule deep in the bulk, by contrast, is pulled equally from every direction. That imbalance is the microscopic origin of surface tension. The bulk is uniformly happy. The surface layer is being yanked inward, and the surface reacts by contracting as much as it can. Surface tension is therefore a strictly surface phenomenon. Only a layer 1 molecule thick is missing its full set of neighbors. Now we put numbers on the pull. Imagine dipping various objects into a liquid and pulling them out. The force you need to apply, minus the object's own weight, is just the surface tension times the total length along which the film contacts the object. The pattern is simple. Number of contact lines times the perimeter. For a thin ring of radius r, the film contacts along the inner and outer circles, so the upward force is 4 pi rs plus the weight of the ring. For a circular disc, only the outer edge touches, so it is 2 pi rs plus w for a square frame of side A. All 4 sides on both faces count, giving A to s plus w. For a square plate, just the outer rim on one face, so 4s plus w. A hollow disc with inner radius r1 and outer radius r2 gives 2 pi times the sum, plus w. And a straight wire of length L, pulled out with a film on both sides, takes 2ls plus w. The diagrams on screen show the geometry for the first 4 cases. The takeaway is that the factor in front of s is always a perimeter, counted once for each side the film touches. Surface tension is not a fixed number for water. It shifts with conditions, and the trends are worth memorizing. Raise the temperature and S decreases, dropping to 0 at the critical temperature where there is no distinction between liquid and vapor. At the boiling point, S is therefore exactly 0. At the freezing point, S is at its maximum for that liquid. Now, impurities. A partially soluble impurity like soap or detergent sits at the surface and weakens the cohesive bonds there, so S decreases. A highly soluble impurity like salt in water strengthens the surface cohesion, so S increases. A film of dust or oil on the surface also drops S, charging a soap bubble grows its size because S itself drops due to electrification. And under weightlessness, surface tension is still present, but a capillary tube no longer shows a height difference because gravity is what supports the column. Beyond all of this, there is a single bookkeeping rule. Whenever you stretch the surface of a liquid, you are working against surface tension, and that work is stored as surface energy. The extra energy equals S times the increase in area. This one line is the engine for the entire next deck. Drops, bubbles, splitting, coalescence. All of it is just bookkeeping on S times delta A. Before we hand off, 3 threads to carry forward. First, the dual reading of S. It is force per length and work per area. The energy form will dominate the next deck. Second, the balance between cohesion and adhesion. F sub C versus F sub A. The same balance reappears in the angle of contact, where it decides whether a liquid rises or falls in a narrow tube. Third, the molecular range explains why surface tension is purely a surface property. Only a layer 1 molecule thick is missing its neighbors. With these 3 ideas in place, we are ready to do real calculation, which is exactly what the next deck is about. A few quick checks before we move on. First, why is surface tension measured in both newtons per meter and joules per square meter? Because energy equals force times distance, dividing force by length and dividing energy by area give the same number. The SI unit is interchangeable. Second, take a soap film on a square frame of side A. The film has 2 surfaces. How much force is needed to hold a slider of weight W? Each side of the slider touches the film along a length A on both surfaces. So the total contact length is 2 times 4A, which is 8A. The force is A to S plus W. Notice the factor of 2 coming from the 2 surfaces of the soap film. It is the same reason a soap bubble's excess pressure is 4S over R instead of 2S over R. Third, why does sprinkling salt on water increase S while soap decreases it? Soluble ions like sodium and chloride strengthen the cohesive pull between water molecules at the surface, raising S. Partially soluble organic impurities like soap sit at the surface and weaken those cohesive bonds. Lowering S. The sign and magnitude of the impurity-water interaction is what decides the direction. Pulling a liquid surface outward stores potential energy, represented by the formula E equals S times delta A. Whenever surface area changes, the energy changes by S per unit area. Because we are dealing with spheres, we use the area of a sphere 4 pi r squared, but we must count the free surfaces. A drop has only one free surface, so we multiply by 4 pi r squared. In contrast, a soap bubble has 2 free surfaces, both inside and outside, so we multiply by 8 pi r squared. Now, if we blow up a drop from radius r1 to r2, the work done is S times 4 pi times the difference of r2 squared and r1 squared. If this were a soap bubble instead, the work done would double because of the 2 free surfaces. In either setup, the work done by the blower is positive and is stored as extra surface energy. A soap bubble is the same calculation with one critical detail. It has 2 free surfaces, the inner film and the outer film. Both surfaces are liquid-air interfaces. So when the bubble grows from radius r1 to radius r2, the total area increase is twice the geometric area change. The work is therefore S times 8 pi times the difference of r2 squared and r1 squared. That factor of 2 is the entire story, and it is the same factor of 2 that shows up again when we talk about the excess pressure inside a soap bubble. The rule from now on is simple. Count the surfaces, then apply the formula. Now consider splitting one big drop into n smaller drops of equal size. Volume must be conserved, so n times 4/3 pi r cubed equals 4/3 pi r cubed, where r is the original radius. Solving, r equals r times n to the minus 1/3. Each small drop has a much smaller radius, but there are n of them, so the total new area is n times 4 pi r squared. The work done in creating all that extra surface is 4 pi s times the difference between n r squared and r squared. Using the volume conservation relation, that simplifies to 4 pi s r squared times the quantity n to the 1/3 minus 1. Because n to the 1/3 is greater than 1 whenever n is greater than 1, the work is positive. Splitting costs energy because total area goes up. The reverse process is coalescence. N small drops of radius r merge into one big drop of radius r. Volume is still conserved, so the same relation r equals r over n to the 1/3 still holds. But now the total area goes down, so the change in surface energy is negative. The system releases energy. The expression is delta U equals S times 4 pi times the difference between n r squared and r squared, which simplifies to 4 pi sr squared n times the quantity 1 minus n to the minus 1/3. Energy leaves the system. It shows up as heat and the bulk temperature rises slightly. For falling raindrops, this tiny heat release is one of the small contributions to drag. The general lesson is worth restating. Increase area and you put work in, decrease area and energy comes out. Always conserve volume. We turn now to the pressure jump across a curved surface. The rule, known as the Young-Laplace result, is that the pressure on the concave side is always higher than the pressure on the convex side, with a magnitude depending on curvature and the number of free surfaces. For a plane surface, the difference is 0. For a liquid drop or an air bubble inside a liquid, both having one free surface, the jump is 2s over r. For a soap bubble in air, which has two surfaces, it is 4s over r. For a cylindrical liquid surface with only one curved axis, the result is s over r for a surface with two unequal principal radii. The full Young-Laplace form is s times the sum of 1 over r1 and 1 over r2, which doubles to 2s times the sum for a soap film with two surfaces. The diagrams below illustrate how these geometric relations translate to physical forces. In the first diagram of a flat surface, the lack of curvature means pressure is balanced on both sides, so delta P is 0. In the curved geometries, the arrows represent the excess pressure, showing how it acts outward from the concave side to balance the contracting force of surface tension. For the cylinder, you can see the curvature exists in only one direction, explaining why its pressure jump is half that of a spherical drop. Finally, the lens-shaped diagrams show how the overall curvature dictates the pressure jump, visually demonstrating that surface tension acts as a pressure per unit curvature. Let's compare the internal pressure of a water drop versus a soap bubble of the same radius. A water drop has only one liquid-air boundary, which creates a pressure difference of 2s over r. A soap bubble, however, consists of a thin liquid film with air on both sides, which gives it two boundaries. Since each boundary contributes 2s over r, they add up to a total pressure difference of 4s over r. With the same surface tension and radius, the bubble has twice the pressure difference of the drop. This is exactly why you have to blow harder to inflate a soap bubble than to grow a water drop of the same size. Now a beautiful contrast that often catches students out. The situation of spraying a liquid and the situation of coalescing droplets are governed by the exact same algebra, but the energy sign is opposite. In spraying, one big drop of radius r breaks into n droplets of radius r equal to r over n to the 1/3. Volume is conserved, total surface area grows, so work is being put in. The expression is 4 pi sr cubed times the difference of 1 over r, and 1 over r, the temperature change of the bulk, is delta theta equals 3s over j times that same difference, and the temperature falls. The spray cools. In coalescing, n small drops merge into one bigger drop. Total surface area decreases, so the surface does work on the surroundings, energy is released as heat, and the bulk warms up. The temperature change has the same numerical value, 3s over j times 1 over r minus 1 over r, but with the opposite sign. The same expression, the same physics applied in opposite directions. Cooling an aerosol and warming a coalescing cloud are the same law, read forward or backward. This slide explores the coalescence of two bubbles. When two bubbles of radii r1 and r2 coalesce isothermally to form a single bubble of radius r, we get a clean geometric identity. R squared equals r1 squared plus r2 squared. In the diagram on the bottom left, we see this process visualized as a pink bubble of radius r1 and a green bubble of radius r2 combine into a final blue bubble of radius r. On the bottom right, we see the case of the common interface where these two bubbles meet, showing the pink bubble and green bubble joined at a dashed boundary. It turns out that this same relation, r squared equals r1 squared plus r2 squared, also fixes the radius of this common interface. We will derive this relation from the interface diagram in the next slide. Take two soap bubbles of radii r1 and r2 sitting in contact with each other. They meet along a common interface, which has its own radius r. To find that radius, balance the pressures on the two sides of the interface. Inside the smaller bubble, the Laplace pressure 4s over r1 is larger than the Laplace pressure inside the larger bubble, 4s over r2. The pressure difference pushes the interface toward the larger bubble, which is why the meniscus curves into the larger bubble. Setting the two pressures equal gives 1 over r equal to 1 over r1 minus 1 over r2. Or equivalently, r equals r1 r2 over the difference r2 minus r1. For r to be positive, r2 must be larger than r1. In words, the small bubble's higher internal pressure bows the interface inward, into the larger bubble, and that is the physical reason behind the algebra. Finally, let's look at using coalescence as a measurement tool. First, if two bubbles of radii R1 and R2 coalesce isothermally to form a single bubble of radius R under external pressure P0, we can solve for S from the energy balance. S equals P0 times the quantity R cubed minus R1 cubed minus R2 cubed, divided by 4 times the quantity R1 squared plus R2 squared minus R squared. Next, the internal pressures at each stage are P1 equals P0 plus 4S over R1, P2 equals P0 plus 4S over R2, and P3 equals P0 plus 4S over R. And finally, the isothermal ideal gas balance gives P1V1 plus P2V2 equals P3V3. This is one of the few ways to measure S from a single coalescence experiment. 3 checks before we move on. A soap bubble of radius 2 centimeters has S equal to 0.03 newtons per meter. What is its excess pressure? Delta P equals 4S over R, which is 4 times 0.03 divided by 0.02, which is 6 pascals. Notice the factor of 4 coming from the two free surfaces. Next, one big drop of radius R is split into 1,000 equal droplets. By what factor does the total surface area increase? Volume conservation gives R equals R over 1,000 to the 1/3, which is R over 10. The new total area is 1,000 times 4 pi R squared, which equals 10 times 4 pi R squared. So the surface area grows by a factor of 10. Finally, why does a curved liquid surface always have higher pressure on its concave side? Because surface tension pulls the membrane inward, like a stretched drum skin. On a curved surface, that inward pull has a net component pointing into the concave side, so the fluid there must push back with a higher pressure. On a perfectly flat surface, the pulls cancel and there is no jump. In the last deck, we saw that liquids want to minimize their surface area. Now, let's look at what happens when a liquid meets a solid wall. The angle of contact, theta, is the angle between the tangent to the liquid surface at the point of contact and the solid surface, measured inside the liquid. This angle is determined by two competing pulls. The cohesive force, F sub c, pulling a surface molecule sideways into the bulk liquid, and the adhesive force, F sub a, pulling it toward the wall. The balance between them sets the angle. If the adhesive force is stronger than the cohesive force divided by the square root of 2, theta is less than 90 degrees, the meniscus becomes concave and the liquid rises. This is exactly what is illustrated in the diagram for water against a glass wall. The strong adhesive pull draws the water up, creating a concave meniscus with a contact angle theta that is clearly less than 90 degrees. If the forces are balanced, theta equals 90 degrees, forming a flat meniscus. If the adhesive force is weaker, theta is greater than 90 degrees, creating a convex meniscus where the liquid falls. Some numbers are worth memorizing because you will see them again and again. Pure water on clean glass has an angle of contact of essentially 0 degrees. Ordinary tap water on glass sits closer to 8 degrees. Pure water on silver has an angle of exactly 90 degrees. Alcohol on clean glass is again essentially 0. Mercury on glass is the famous outlier at 138 degrees. 3 trends to keep in mind. The angle of contact depends on the nature of the liquid, the nature of the solid, and the medium sitting above the free surface. It increases with temperature, and it decreases when a soluble impurity is added to the liquid. A neat demonstration of the last point: coat a glass tube with wax and water no longer wets it. The angle becomes obtuse and water falls in the tube instead of rising. Let us put the 3 regimes side by side. When theta is less than 90 degrees, as with water on glass, the meniscus is concave, the liquid rises in a capillary, the solid is wetted, adhesive force exceeds cohesive force divided by root 2, and the free surface curves up to nearly a half sphere at the wall. When theta is exactly 90, the meniscus is flat, there is no capillary rise or fall, the liquid neither wets nor beads, and adhesive force equals cohesive force divided by root 2. When theta is greater than 90, the meniscus is convex, the liquid falls in a capillary, the solid is not wetted, and adhesive force is weaker than cohesive force divided by root 2. The 3 lines of this table are not just textbook categories. They correspond to the 3 everyday liquids: water, water on silver, and mercury on glass. Now we put a number on the rise. Capillarity is the rise or fall of a liquid column in a narrow tube, and the height h is given by h equals 2s cosine theta divided by r rho g minus a small correction of r over 3. The quantities are the surface tension S, the angle of contact theta, the tube radius r, the liquid density ρ, and gravitational acceleration g for a very narrow tube, the correction term r over 3 is negligible, and the formula simplifies to h equals 2s cosine theta over r rho g. Two cases are immediate. If theta is less than 90, cosine theta is positive and h is positive, meaning the liquid rises. If theta is greater than 90, cosine theta is negative and h is negative, meaning the liquid falls. Notice the physical balance. The rise or fall lowers the gravitational potential energy of the bulk liquid by exactly the amount needed to pay for the new surface area created where the liquid wets the wall. Energy is conserved. This single equation shows up at wildly different length scales. In a lantern or a candle, kerosene and melted wax climb the fine capillaries of a cotton wick and burn steadily at the top. In a cup of coffee, water wets the fine granules of coffee powder almost instantly, because the very small radius of the pores inside the granules gives very strong capillary suction. In a plant, water taken up by the roots rises through countless capillaries in the stem and reaches every leaf. Three very different settings, but the same proportionality H proportional to S over R rho G at work in all of them. Let's consider two special capillary cases. First, if a capillary tube is shorter than the equilibrium height, the liquid won't overflow. Instead, it stops at the tube's rim by forming a flatter meniscus with a larger radius of curvature, R. This is governed by the constant product R times H, meaning a larger radius of curvature compensates for a shorter column height. Second, let's examine the diagram comparing the vertical capillary on the left to the inclined one on the right. When the tube is tilted at an angle alpha from the vertical, the length of the liquid slug along the tube, labeled L, increases such that L equals H over cosine alpha. However, as the horizontal dashed line spanning across both tubes illustrates, the vertical height h remains exactly the same. This visualizes why only the vertical rise matters. It is the vertical height that determines the hydrostatic pressure supporting the meniscus. Thus, tilting the tube allows it to hold a longer liquid column while maintaining the exact same vertical height and pressure equilibrium. A quick catalog of where this physics shows up in the real world. Dettol and similar antiseptic liquids have a surface tension lower than water, so they spread into every crevice of a wound instead of beating up. Hot soup has lower surface tension than cold soup, so it spreads over more of the tongue and tastes stronger. Insects such as water striders and mosquito larvae sit on a film held up by surface tension. Spraying kerosene on stagnant water lowers the surface tension so much that the insects sink, which is exactly why kerosene is used as a mosquito control. Push a hanging drop sideways and it rounds up again, because the surface keeps minimizing area. And detergents clean clothes because detergent molecules bind to both water and dirt, lowering the local surface tension and letting the dirt be lifted off the fabric and carried away. A few quick checks. Why does mercury fall in a glass capillary while water rises? Mercury has an obtuse angle of contact with glass, around 138 degrees, so cosine theta is negative. In H equals 2s cosine theta over r rho g, that negative cosine theta makes H negative, so the mercury column sits below the level outside with a convex meniscus. Water on glass is the opposite case. Next, a capillary shorter than the equilibrium rise is dipped in water. What does the meniscus look like? The water does not overflow. The meniscus flattens, its radius of curvature grows, and the column shortens until the product R times H matches the Jurin's law constant. The angle of contact changes from its natural value to whatever is needed to satisfy the available height. Finally, why does hot soup taste stronger than cold soup? Hot soup has lower surface tension, so it spreads more easily across the tongue, contacts more taste buds, and produces a stronger flavor signal from the same amount of soup. Let us step back and gather the four big ideas of this whole series. First, surface tension is force per length and energy per area. S equals F over L equals W over delta A, same number, two physical readings. Second, curved surfaces store extra pressure. Delta P equals 2S over R for one surface, 4S over R for a soap bubble, and S times the sum of 1 over R1 and 1 over R2 for a non-spherical surface. Third, cohesion versus adhesion decides wetting. F sub A greater than F sub C over root 2 gives theta less than 90 and the liquid rises. F sub A less than F sub C over root 2 gives theta greater than 90 and the liquid falls. Fourth, everything is bookkeeping on S times delta A. Drops, bubbles, splitting, coalescence, all conserve volume and minimize area. A few traps to carry forward. Ignore the R over 3 correction only for genuinely narrow tubes. Soap bubble versus drop, same S and R, but the pressure jump differs by a factor of 2 because of the extra surface. Splitting a drop is endothermic. Coalescing drops releases energy and warms the bulk. The same delta theta expression describes both spray cooling and coalescence warming with opposite signs, and Jurin's law uses the radius of curvature of the meniscus, not the tube radius. Confusing the two gives the wrong scaling. A few takeaways that transfer beyond this lesson. Minimization principle. A surface under tension behaves like a stretched membrane and picks the configuration that minimizes area. The same principle generalizes to minimal surfaces in mathematics and to vesicle shapes in biology. Count the surfaces. Anytime a formula has 2 versus 4 or 1 versus 2 for a soap bubble versus a drop, ask how many interfaces this object has. That single question resolves most of the apparent contradictions in this chapter. Geometry drives pressure. The smaller the radius, the bigger the pressure jump. That is why alveoli in the lungs, droplets in clouds, and bubbles in boiling water all behave so differently from their flat surface counterparts. Hold these 3 ideas and the rest of the chapter fits inside them. To go further, here are 3 high-trust resources. For a free, rigorous first principles derivation of the capillary formula, look up the MIT OpenCourseWare lectures on fluid mechanics. For the deeper thermodynamic picture and the Young Laplace derivation, see Halliday, Resnick, and Walker, Fundamentals of Physics in the chapter on fluids. And for a visual tour of minimal surfaces and soap film geometry, search for Plateau's laws, the same surface tension physics applied to soap films spanning wire frames. This lesson is part of the Fiscribe YouTube channel, where we turn dense physics material into short, precise slide-based lectures. Subscribe for the next chapter in the Fluids series.